Okay, so we're going to move on to section 10.2, calculus with parametric curves. So this is part one. So the first problem we're going to think about is, if I have a set of parametric equations, x is equal to f of t, y is equal to g of t, and these things are going to look, however crazy you want them to look. But the problem is, if I wanted to find the slope of the tangent line at one of these points, how would I go about doing that now that I have, instead of an implicit or an explicit equation, I have these parametric equations. So that's the question. So the question is, how do I find slopes of tangent lines of parametric curves? And the answer is going to be chain rule. What I mean by that is, what I'm trying to find is dy dx. And to do that, I'm going to first think about, okay, what is dy dt? Well, dy dt is going to be equal to, by chain rule, dy dx times dx dt. You think about the way you think about chain rule, and this is a mnemonic device, it's not anything rigorous, is, if these things were fractions, you would be able to cancel the dx's out, and you would be left with just dy dt. So that's how you remember, remember how to do chain rule like this. And this gives me, if dx dt is not equal to 0, then I'm going to be able to divide by it, and I'll find dy dx is equal to dy dt divided by dx dt. That is, again, if dx dt is not equal to 0. I'm not allowed to divide by 0. And so let's just take a moment and note a couple things. If dy dx is equal to 0, just like before last semester, we have a horizontal tangent line. And so that'll happen. So that'll happen when dy dt is equal to 0 and dx dt is not equal to 0. If you look at this equation here. So if dx dt is equal to 0 and dy dt is not 0, then you can look at this equation for dy dx and say, okay, the tangent line is undefined there. This is a vertical tangent line. We have a vertical tangent. And we're going to be using that. We have two examples for this section. The last thing I'm gonna do is the second derivative. So I'm gonna make this a short video because the example for this one is kind of long. So for the second derivative, what I'm trying to calculate is d squared y dx squared. And your first thought might be, okay, just take the equation I have, make everything a second derivative. That doesn't work here. So what I have to do is I do ddx of dy dx, which is just another way of writing the second derivative. I haven't done anything. And so what I'm going to do now is I'm going to take this ddx of dy dx, and I'm going to use this first equation here and figure out what that is. So instead of, a y that I'm taking the derivative of, I'm taking dy dx. So I'm just going to replace all my y's with dy dx's, and that's where I'm going to get this equation from. This is going to be ddt of dy dx over dx dt. And that's going to be my formula for the second derivative. D squared y dx squared is ddt dy dx over dx dt. And again, all I'm doing is I'm taking my formula for dy dx and plugging dy dx in for y. So, you'll have to, case by case, just do this part. But we'll see an example of how to do that. So I'm going to actually stop this here. I know this is a short video. That's on purpose because this example takes a little while to do. So we'll jump into example 1 in the next section.